Yo, yo! Yo, yo! Man, I am screwing this up big time. I've just been talking for like the last five minutes and I just realised I didn't click start stream. Okay, how's it going? How's it going, guys? How's it going, guys? Yeah, I did the countdown for the stream and I was like, yo, hey guys, how's it going? And I hadn't clicked start stream yet. So even though I'd started streaming in OBS, I hadn't clicked start stream on this page here. This is little start stream, end stream button. Had not clicked on that. So therefore I was talking to myself. Evening, guys. Evening, guys. So this evening we're going to be doing a short stream. I'm absolutely exhausted. I haven't been going to bed till like 4 or 5 a.m. Began up at like sort of 10, 11. Not much sleep the last few days. I've been out in London all day, the centre of London. Been doing some Christmas shopping and a few bits and pieces. Absolutely busy day. Came home, just wanted to sleep, but I had some work to do anyway. So I thought I'd come down here and do a quick stream just to show you a couple of bits. Yeah, doing good. I'm absolutely exhausted though, man. Thank you very much, Matthew. Absolutely exhausted. So guys, I'm going to jump straight into it because I want to get the stuff sorted and get to bed. So on the bench this evening we have a very similar amplifier to the to the B2 audio. It's right at 16K that I've been doing a couple of videos on recently. This is the ground zero version. It's the same circuit, it's the same Sound Digital. These are actually made by Sound Digital, these ones, as opposed to the Riot, which are I think the Chinese copy. Yeah, this is the 12K ground zero version. And this one came in with a single dead MOSFET in the power supply section. The MOSFET in the power supply section actually had like a blown open leg. One of the legs of the MOSFET was completely blown open, which is pretty unusual. I guess maybe just too much current was drawn from the power supply in a kind of burst or in like a pulse, and the leg with, or the part of the power supply with the highest resistance ended up being that leg of one of the MOSFETs, which then fused open like a fuse. So yeah, pretty interesting failure mode there. By removing that MOSFET, the amplifier came on and worked perfectly fine. Now, I didn't want to just replace that one single MOSFET. I didn't know whether the other MOSFETs in the amplifier as a whole had been stressed, or had been damaged potentially by that single MOSFET failing. So I didn't want to just replace the one bank, or didn't want to just replace the one MOSFET. So what I had to do was I had to replace all 24, I think it is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, yeah, all 24 of these power supply MOSFETs, and you can't get the original ones anymore, or you can if you import them from America, and they're very expensive. So the MOSFETs that I've chosen are replacements which have a slightly higher gate capacitance and slightly higher gate charge than the originals. Now, the thing that's interesting about this amplifier, and the reason that they use the specific FETs that they do, is because this whole amplifier, this whole power supply section, is being driven by a single tiny little drive IC right here. So this drive IC is powering every single one, it's driving every single one of those MOSFETs directly. So we don't want too high gate charge on the power supply MOSFETs, because it's going to put stress and pressure on that little driver there, which we don't want. So I tried to find the power supply MOSFETs that had similar enough drain current and power handling and on resistance to the originals, but that had a low enough gate charge and input capacitance that it wouldn't stress the little drive chip too much, which is labelled as an IR4427, which is absolutely nonsense. That's not what it is at all. Don't know why they labelled it as that. So the first thing I want to do, I have just stripped this amplifier of all the power supply FETs, loaded in 24 brand new ones. This amplifier worked before I stripped the power supply FETs. Like I say, it worked fine with just the one power supply MOSFET that was bad taken out. So there's no reason this amplifier shouldn't work. So I'm just going to power it on now, and I'm going to power it on, and we're going to use our thermal imaging camera to make sure that the drive IC over here isn't getting too hot as a result of the slightly higher gate charge MOSFETs that we've used this time. And I want to make sure that the FETs don't heat up. I want to make sure that the drive wave shape is good on these replacement FETs. This is so annoying, this. I need to replace the internal battery, I think. So let's first of all just get it powered up. Let's make sure that it still runs and nothing's changed about it while it's been sitting on my to-do list bench for a while. So let's give you the scope screen. We are going to pulse the power supply a little bit. We should see a couple of pulses pop up on the screen here. Helps if I plug my remote wire in there, doesn't it? The remote wire on this one is just around here. There we go. Yep, so you can see there are a couple of pulses. So if we zoom right in, you can see, you can just about make out a couple of pulses coming in there. Yeah, I mean, they're so fast and they're so instantaneous, the scope doesn't really get a chance to kind of read them. But we should start building rail voltage, which we are. We have 35 volts on the main rail, and on the half rail floating output ground, we have 10.5 volts. So I'm going to take my second oscilloscope probe now. Now that I know we're building rail voltage, which is a good sign, I'm going to get this this second scope probe, and I'm going to clamp it onto something that has the full rail on it, which I'm probably going to choose as this one. Let's reset all of my scope parameters, clear messages. We're going to go for channel 1 volts RMS, then we want channel 1 frequency, and channel 2 volts RMS as well. That's back to normal, so we have 32.9 volts on channel 2, 10.6 volts going in, and we want to make sure that output switching comes to life, and then we can check the health status of the power supply MOSFET drive waves. So I'm just pulsing the remote now to get the rail voltage built up nice and high. Let's feel the power supply MOSFETs with my finger here just quickly, just to make sure that none of them are heating up with these small pulses that we're giving it just now. Shouldn't be. We now have 94 volts on the main rail here. And this is still feeling pretty good. So now we're going to try and power it on fully and check low side drive, which is going to be on 1, 2, we've got 1, 2, 3, 4, 1, 2, 3, 4, so it should be on some of these ones. Here we go, amplifier's coming on fully. So let's see then. I'm really scared. It should work absolutely fine. There's no reason it shouldn't work, because it worked before, but I always hate turning these fucking amps on. Reject low frequency. There we go. Okay, 5.7 amps drawn. And what does the power supply wave look like? That is the most important thing here. It's kind of all over the place. Okay, that's our power supply drain wave. It's a bit noisy on the scope screen there. It could be because we have a floating output ground. I am a bit too tired to bother, worrying about that. I just want to make sure that the power supply FETs are being driven properly. So what we have here, we have no heat on the power supply FETs. I want to just check that the gate driver for the power supply isn't getting crazy hot from driving these slightly higher gate charge FETs. Doesn't seem like it is, which is cool. So let's go back to the scope and let's power it up a bit more and turn the voltage up to 12 volts and make sure that we have good gate drive. So I'm going to take my oscilloscope probe clip here. I'm going to clip it onto one of the power supply MOSFET gate legs, because I want to read the gate wave, see what that looks like on the scope probe here. There we go. Get this nice and zoomed in on here. Let's go for full power up again. Yeah, we've got a bunch of noise on the scope here. I wonder if I can, do we have a floating output ground? Probably not. Bunch of noise here, but never mind. Oh, I probed, this is how tired I am. I just probed the freaking source instead of the gate. Ah. Get it together, man. Probe the gate instead of the source, that should help. Power it up again, here we go. Okay, there's our fuck ton of noise, probably due to how my scope is being grounded. So let's see if we can ground our scope a little better to this amplifier then. I don't know why the ground quality between my scope and power supply seems to have diminished quite considerably. What's the resistance here between my ground scope, my scope ground, and my main power supply ground? 1 ohm. That's a little high. Yeah, so I think whatever the ground is between them has slightly diminished. So I'm just going to use this little ground wire. I'm going to use this to ground onto the main ground of the amplifier over here. It's going to be this one just here. That should help out with that noise a little bit. still very noisy. Noise rejection on off, nope. So the actual wave, the actual MOSFET drive wave isn't this noisy. It isn't actually this noisy in real life, but it's just something to do with the amplifier switching that's causing the noise. But that is a very good looking drive. That is a very good looking drive on the power supply, so I'm happy with that. Now let's take our thermal imaging camera, just make sure that we are not getting crazy hot on that driver. Okay, we're at 36 degrees, looks like. 42, 41, 42 degrees. Let's go up to 12 volts. We have 177 volts on the rails. The driver's at 46 degrees Celsius. Okay, so we've not got any scary, crazy high temperatures here. Just 47, 48, 49 degrees on the driver IC. That's acceptable. When you've got the amplifier in the case, you'll have some airflow from the fans blowing over it. So I think that that's absolutely fine. So yeah, that's this amplifier done and dusted. I just wanted to check that, confirm everything was okay. Let's read a little bit of live chat while that voltage is sinking down. 176 volts on the rails, kind of high. Is it the same interior as the B2 right? Yes, it's exactly the same amplifier. It's just a smaller version. This is the smaller version using TO220 package MOSFETs as opposed to IGBTs in the output section. Yeah, small power supply FETs there. SnapX, yo, how's it going? Matt, what's up, my man? Promo. Mike Honda, good to see you guys all here. Henrik, quick roundup. Yeah, so just quickly started the stream by just confirming that my repair on this amplifier was solid and good to go. Whew, my chest is killing me today. So I'm just gonna sink this voltage down to ground real quick, and then we're gonna look at a small Pioneer amplifier and see what the issue with that is. Just find out where do we have our positive rail voltage. Okay, all the way up here. There we go. Did you see that on the scope screen? Rail voltage is now sunk down to ground nicely, so I can safely handle the amplifier now, remove all of my probes and whatnot from here. All the power wires, etc. Don't even know where my Allen key is. Okay, so I shall pop that back in the case tomorrow, ready for the customer. I'm glad that those power supply FETs that I chose seem to be okay. That was a bit of a risk choosing those, but they seem to be very, very happy. But I'll run some more tests with it tomorrow. Now, for this evening, we're gonna look at this tiny little baby Pioneer GMD 8601. These are fantastic amplifiers, guys. Pioneer are really knocking it out the park with value for money on these things. These amplifiers are incredibly well designed, very well built, and they don't cost much at all. They're very, very cheap amplifiers. Someone has busted a screw in there. These are very, very cheap for the quality of what's inside and the circuit design and the components used. So I do recommend these to a lot of people looking for, you know, between 800 to 1200 watts RMS at 1 ohm Class D subwoofer amplifier. So let's have a look what we got in here. Now this is the 8601, which I think is about 800 watts RMS at 1 ohm. We have a primary inductor here, which is sitting on the 12 volt line coming from the vehicle's battery in, which is fantastic to see. It's not going to be sending too much noise back down the amplifier, the car system. Now actually, just before I go on, what I've already noticed is actually, this camera isn't working, but that's fine. I've already noticed that we have a small strand of wire, speaker cable, just chilling in here. Now this is a common cause of fault with car amplifiers when you're trimming your cables and they get inside the amplifier and they short something out. So that could be what happened. Oh, there's a whole bunch of them in here. Look at another big one there. There's a big boy. Big strand of wire. This is common cause of failure. There's another one here. All over the show in here, these strands of wire. So I wouldn't be surprised if that's why this one is in the workshop this evening. User error. Strands of wire inside the amplifier, shorting stuff out. Let's have a look then, take a look. So yeah, we've got a decent sized transformer for the size of amplifier for the power rating. Nice size transformer. We've got the primary inductor. Power supply filter caps are adequate. We have 32 IRF 3205 power supply FETs. 1, 2, 3, 4, 5, 6 of those. 3 push, 3 pull on the transformer. Rail capacitors, we have a really decent amount for the size of amplifier. This is, again, we have the input filtration circuit, which is using decent quality op amps in the filter circuit. We have some film capacitors there as well for the signal passing, and we have a drive circuit consisting of an IRS 2092S with output buffer transistors as well, which is pretty awesome. And in the output section, we have IRF, IRFB 4227, I think these are output FETs, which we'll probably discuss in a minute. And these are bloody awesome for this budget and size of amplifier. Okay, so primary findings then. We don't seem to have any shorted output FETs. Do we have shorted power supply FETs? It would appear that we do not. Okay, cool. So now let's power the amplifier up. Now that we've confirmed we don't have any shorted FETs, we can safely power the amplifier up and see what's going on and why is it in my workshop. Okay, power supply coming on now. We don't have any shorts, don't have any current draw at idle without the remote going in, so let's crank the voltage down a touch. Current limit to about 4 amps. Voltage on the scope down to 20 volts divide. We're going to just pulse the remote a couple of times to get some voltage in this board. There we go, just pulse the remote there, get a little bit of rail voltage built. So we have low side MOSFETs looking good with negative rail, 0 negative rail on the FET, and high side we have 0 positive rail, 0, which is good. That is exactly what we want to see. Now we can power the amplifier up fully and see if we get switching on the low side drain. Oh, it's trying. Alright, there we go. So we do have switching on the output section. So why then is this amplifier in my workshop? Perhaps it doesn't pass any signal. Perhaps if we plug our signal generator in here, perhaps there is no sound, there's no audio. So let's go ahead and let's shove in maybe something like 40, 50 hertz, something like that. I need to do some maintenance on this signal generator. The potentiometer for selecting frequency is very all over the place. I need to replace that. Gain is already down at 0, which is unusual. Okay, cool. So now we've got 47 hertz going in, so let's see, do we have 47 hertz coming onto the outputs? I would say yes we do. So this amplifier is working just fine. Why did you send it in then? Okay, never mind. This one's fine. Any vibration issues? So if I tap the transformer, you can hear it ringing there. That's pretty normal. Any issues if I bang the board anywhere, perhaps? No, seems fine. Alright, well, never mind. I'll do some more tests on that later, but that seems fine. No point covering that in a repair because it's doing everything it's supposed to do. On to the next one. But what I will do though is I will freaking get anything that's like loose floating around in there. Maybe something was just kind of floating around in there, just like shorting out across the protection circuit, causing it to go into protection. You saw how many strands of wire there were in there, so that might have been what was happening, and now that piece of wire has been dislodged and therefore no longer shorting. Okay, next one then is we have this kind of big boy. This kind of big boy over here. Oh yeah. This is a Fusion PP Bus G3 Hot. No, this is not a PP Bus G3 Hot. This is a PP AM 1240. So this, I believe, is a 4-channel. Yes, this is a kind of cheap budget Fusion 4-channel thing. Nothing particularly special. Let's take a quick look inside, check out the guts, see what we've got going on in here. I believe we're just going to have like a nice, cheap, nasty Chinese single layer PCB 4-channel Class AB. Yeah, what did we say? So single layer PCB, very, very bouncy, flexible board, nice for snapping legs on components. We have blown power supply MOSFETs by the looks of things. And we also have very loose screws. They were very, very loose in there. As are these. Look, I've only done one screw so far. And this is already like completely coming off, so this has been vibrated to bits. So perhaps we have vibration damage somewhere else. Wow, these are freaking cooked, man. These are properly cooked. Properly cooked. These are IRFZ 84V. The other, actually it could have been that someone, you know, already took that off to have a look and see what was going on. This should be a nice quick repair, he says. Should be a nice easy boy power supply repair. Not all of the amplifier repairs are difficult and headaches like the Hertz and stuff. Some of them are kind of easy boy. Well, that's interesting because that's undoing a screw very difficultly. Why is that screw like struggling to be undone? Couple more screws over this side. Any more over here. Got a couple of thermostats, what it looks like over here for thermal protection. Let's get those out of the way. Any screws down the center, doesn't look like it, so we're good. So now we just need to take the ones out the side. And to get to the side ones, we've got to take this beauty plate off first. Beauty plate comes off. End panel. Has some cheeky Allen keys on the top too. Get a slightly bigger one for that. Nope, it's in between sizes, probably because it's an American or a Asian size. So we're going to go with our security bolt bit, which actually works fantastically for these in-between size Allen keys. Works a treat on these. Missed a screw by the output fence. Nope, that was one that would not undo, so we're just going to have to kind of pull that out. Sam, speaking of fusion, do you still have that 450 watt fusion from back in the day? No, absolutely not. I sold that years ago. You know, once I realised that it wasn't actually any good, I got rid of that pretty pronto. No reason for me to have that chilling around. Okay, we should come out now. There's one screw here that doesn't want to undo for some reason. It just kind of spins, and it's still got quite a bit of. There's a couple more screws. Two more at the top here on the case. Here we go. Okay. Hopefully, I don't have to remove the thermistors over there. This is the screw that I'm a bit worried about, which might cause us some problems. You know what, screw it. Let's just remove this thermostat. So because we have this screw here that doesn't want to come out, what we're going to have to do is to bend all of these towards us so we can lift this out of the case rather than slide it out, because the screw obviously is not going to slide itself out of the case because it's still wedged on something under there. So we're just going to pull all these output transistors forward ever so slightly like this, and it should come out upwards, and we should be able to pull that screw out of the thread that it's stuck in. There we go. Sweet, we are free. Right, so yes, dead power supply section then. Let me see if we can just get this camera working real quick. What are we on? JVC, so let me just refresh this one. Deactivate when not in use. Turn off and turn on. Nope. Still doesn't want to come to life. Oh wait, here we go. It's green. Excellent. Love it when it's green. There we go. That's better. Off and on a couple of times. If it doesn't work, have you tried turning it on and off a couple of times? Usually fixes the issue. Right, power supply FETs then, gentlemen. As always, we have 1, 2, 3, 4 over here, which look pretty in bad shape. And we have 1, 2, 3, 4 over the other side. Again, pretty bad shape. Let's get rid of these stanky boys from the board. Check the drive circuit. Now, in terms of the drive circuit, I reckon is going to be okay. Do you know why I think that? I think the drive circuit is going to be okay because the gate resistors are not burned. That's not a guaranteed thing, but generally, if the drive circuit has been burned, has been killed by the 12 volts feeding back through the PNP transistor, then the gate resistors will, you know, they'll be pretty badly burned as well because they would have had the current drawn through them. But these are 10 ohm gate resistors, which are low value gate resistors, which will burn very easily. I think actually no, they might be 100 ohm actually. I think these might be 100 ohm gate resistors, which would explain why they probably survived because they're nice high resistance. Yep, sorry, 100 ohm resistors. That's brown gold, not brown black gold. Didn't look close enough. So 100 ohm gate resistors then. So yeah, the drive circuit probably survived, but we don't know the cause of failure for the power supply section. It could just be that the amplifier was, you know, pushed too hard and that they've just been overdriven, or it could be that the drive circuit has itself failed internally, causing the power supply section to go down. So let's start by removing all of the MOSFET legs from the original FETs here. Start preheat the board a little bit. Evening, Jessie. How are you doing? How are you doing, girl? We also have the possibility that the output transistors may have shorted and failed, which killed the power supply. So we're going to have to check that out as well. But I don't know. What do you reckon, guys? What's your bets? What's your bets? Do you reckon the output section died, killing the power supply, or do you reckon the power supply just killed itself on these old amps? Bub. 8 power supply MOSFETs. What shall we replace with? 100 ohm gate resistors. Require something easy to drive. I have loads and loads of spare 65 NF06 FETs. I'm pretty sure those bad boys have a nice low gate charge, which should mean that we haven't got to faff around changing the 100 ohm gate resistors for 47s or 22s or 10s, etc. Which would be nice because this is a cheap low quality amplifier. We don't really want to be spending any more time than we need to getting it back up and running, because at the end of the day, the customer's not going to want to spend out a great deal on repairing this because it's not worth a great deal in the first place. Well, sorry, Labs, how's it going, my man? You caught me on my sleepiest, dopiest, like, jankiest live stream, literally. So apologies for that. The one that you tuned into had to be the one where I'm literally about to fall asleep right now. Not doing anything too exciting this evening, unfortunately. Just some janky old fusion stuff. But I have some pretty cool stuff planned. So maybe come back another evening. We wish the drive circuit survived. We wish the drive circuit survived. We wish the drive circuit survived. Or it's not worth repair. The smoke is in the air. The MOSFETs are on fire. Oh no. The gate resistors burned. I wish I would have learned. Okay, almost all of these dead legs are out, so we can start checking the drive circuit in just a moment. I think this drive circuit only uses a single NPN and single PNP, so that helps. Obviously, the 100 ohm gate resistors will be cool in that regard because you know, it won't stress those drive transistors too hard. Nice slow turn on and slow turn off of the MOSFETs here. I wonder if the dead time is like 50%. It's using a TL494 as opposed to an SG3525. We can vary the dead time with a TL494, but I would say 99% of car amplifiers that I see and work on using a TL494, they are not really regulating the power supply, or they are not setting like a custom dead time. They're just kind of hard switching the FETs. And there will be some switching losses for that, which is something I'm learning about quite quickly. Ouch, I just banged my leg on the table. Oh, that's gonna hurt later. Alright, any solder bridges? I imagine we probably have like 10 or 11 solder bridges because of my current state of awakeness is pretty low. Looks good to me there, looks good to me there. Just got rid of one over there. That's 2 so far. 3, 4, 5. Bevid should start doing an overall virtual view of the amp and have us inspect the amp and do a poll of what caused the amp to fail. See how close some of us get. Yeah, what do you guys reckon for the cause here? Do you reckon output or do you reckon power supply? Google search the audio barn A5K SPL. Says Big D. Alright, let's do a quick Google search, shall we? What's that one saying? Oops. Yes, that's what I need to do. Initial Pro, how's it going? Oh, Wilson Audio. That was for another comment. No worries. But let's check it out anyway. That looks like a car amplifier that doesn't know whether it's a car amp or whether it's a PA rack mount amp from AliExpress. I mean, back in the day, like back in the heyday of kind of sex spec, that would have been pretty darn cool. I imagine rocking that in the back of your whip. I wonder what's inside of it. We've got dual battery power and grounds, single speaker output. Are they actually fans or are they just cutouts? I think they're just cutouts, because if they were fans, I imagine they would have some bolts coming through. Rails, nice big box. We got some guts pictures. Anyone got some guts pictures of this bad boy? Is this a big old Class AB? Oh wait, here we go. What's this? Oh, amperformance.de. They freaking benched it. Awesome. They freaking benched it. Let's see how much power it does. See what it's all about. Come on. Come on, show me the guts, baby. Okay. Ooh. Really? Okay. This literally is a home amplifier / PA amplifier just with a switching power supply. Okay. Interesting. Damn, there's some freaking Sanken. Okay, have not seen those really used in car amplifiers much, apart from here. The good thing about these is the die size is massive, and obviously the case size is massive, so the power dissipation from these parts is going to be absolutely through the roof compared to your TO220 or TO247, 274 parts. Yeah, pretty cool. Yeah, pretty interesting. I mean, compared to like most home or PA amplifiers, this will be a piece of junk, but for a car amp, it's interesting. It makes 1 × 2600 watts RMS at 1 channel. So it's a mono. Okay, at 2 ohm. It's a 2 ohm, 2.5K mono. With a little bit more power headroom with a 14.4 volts. So, damn, fair play. It's a freaking big ass Class AB mono. How do you do? How you doing? Rated 5K at 1 ohm. Jesus, really? I guess that they, so the ampperformance.de guys, they didn't always bench these massive power amps, and they didn't always go down to 1 ohm because the test bench wasn't always powerful enough, especially for a while. Some of the bigger amps you see on their earlier tests, they state didn't test 1 ohm due to power supply limitations, etc. But yeah, pretty cool. Damn, 5K from a Class AB. I got one that's broken. Oh shit, son. Well, to be honest with you, I mean, I've not had a great deal of experience repairing this style of board, but with these kind of Class ABs, right, so the drive circuits in these are going to be beefy as frick. And when an output dies, it's going to swing the speaker terminal to DC, which is going to instantly trigger the protection circuit. So if the output section has failed, if the amplifier still tries to come on but goes into protection, then you should just be safe to just replace those Sanken transistors if you can find replacement for them. If the power supply section is burned, again, that's not too difficult either. You just want to be replacing the power supply MOSFETs that it will be using, and you want to be replacing potentially the drive circuit. That's the only tricky thing. If the drive circuits fail, this gets a little bit more involved. You know, oscilloscope, scope the stuff and work out correct drivers to use and stuff like that. But yeah, man, big D. If you want any assistance, if you want any help in getting that bad boy up and running, give me a shout. I can try and send you some tips over. Right, we're just about to find out whether the drive circuit survived in this hunk of junk. I think it did, because we have 100 ohm gate resistors, and we don't have any burn 100 ohm gate resistors, and the MOSFETs, when they failed, the failure mode was drain to source, like quite badly. The gate legs didn't really look too badly affected, so I can't solder wires, much less components. The only reason that you can't do that, my friend, is possibly just due to your soldering iron. So about 5 or 6 years ago, I could not solder for love nor money. Literally, I freaking sucked, and I thought that it was just a really hard, super hard skill that you needed like loads of like experience in and shit like that. But it turned out that I just couldn't solder because my soldering irons that I only ever tried with were absolute junk. As soon as you get a decent powered soldering iron that gets hot enough, soldering is like, oh hell, it's easy as friggin' anything. It's like so easy because the solder just melts instantly and you just pull the part out, you put the part in and just the solder just melts instantly. It's great, it's very satisfying. Get yourself a nice powerful soldering iron and you'll find that new avenues, new kind of things open up to you that you thought were limitations before, and fixing stuff that you didn't think you could fix before, like soldering shit. It's great. It's great stuff. Okay, drive circuit, what you are saying, my friend? Are you okay? Do we need to make you a replacement drive circuit, or you are okay, no? I'm gonna make a guess at 25 kilohertz on the power supply switching frequency. What you are saying? 25 kilohertz here. Oh, wait, no. Oh. This is not looking so promising. Oh, wait, what about the fuses? Do we have 12 volts at the drain? Oh, shit, we do. Okay, the fuses are fine. Okay, what's going on with the power? What's going on with the drive, then? The drive doesn't appear to be doing anything. Did we lose the drive? Or maybe the TL494 gave up. That's also a possibility in these old ass amps. Okay, so we're drawing 0.1 of an amp, which is never really a good sign. That might not seem like much, but actually 0.1 of an amp is actually quite a lot for just a drive circuit chilling there, not driving any FETs. So I'm gonna potentially guess that we might have a blown either. What's this? Oh, this TL494 feels a bit hot. Maybe the TL494 gave up. What are you saying? TL494. TL494. What are you playing at, my friend? Let's probe the TL494. So we're looking at pins 9 and 10. We're looking for a cheeky square wave on pins 9 and 10. Oh, we have nothing. We have nothing on pin 9 and 10. What about pin 12? We have 12 volts on pin 12. Yep. Oh, we have 4 volts on these ones, which are going to be the 5. What have we got? 4.9. Yeah, so 5 volts. The TL494 has a very accurate 5 volt regulator inside. Oh, we have. So what's pin 3 saying? Pin 3 is low. So pin 3 is low, which means that if pin 4 is up at 3 volts, we do have this oscillation here. So the TL494 should technically be outputting some stuff right about now, but it's not. I wonder if this TL494 might be bad. That's very curious if it is. The drive transistors on the board here are not heating up. The thing that's heating up is the TL494. It's drawing 0.1 of an amp, which it should not be doing. These things draw literally next to nothing. Yeah, these should draw absolutely next to nothing. Oh, check it out. Cheeky flash of the watch. I actually forgot I had my watch on. I don't usually have my watch. I was out in London today, and yeah. So, why are you drawing 0.1 amps here? Oh. Okay, something's maybe getting a bit stanky, so let's take a look at our thermal imaging camera right here. Let's take a look what's actually getting hot. I don't want to be moving my fingers around here, because if something's getting hot, I don't want to burn my finger off. This is so frustrating. The internal battery must be dead, because I have to reset the brightness every time I turn this thing on. Alright, 14.5 volts going in. Something's getting cookie. Something's getting a bit cooked. Not too hot, though. Only reading about 28 degrees on there. I still think the TL494 is KO'd. The way to tell is, okay, so the only reason the TL494 would not be outputting pulses is if it's either KO'd or the voltage is too high on pin 4. So pin 3 and 4 can disable the TL494 from outputting pulses if the voltage is high on those pins. Pin 3 is the output of the comparators on pin 1, 2, 15, 16. So if that goes high, it'll disable the chip in protection mode. But pin 4 is a dead time control. If pin 4, if the voltage is too high, then the dead time will be at over 100% or at 100%. So therefore, we won't get any pulses. So if we take our little ground probe here, we're just going to ground pin 4 and see if the pulses return on pins 9 and 10. Oh, they do. Oh, they do return on pins 9 and 10. So, therefore, whatever the issue is, you can see I'm just kind of like touching and not touching pin 4. Whatever the problem is then is pin 4 is staying high. Pin 4 is not sinking down to ground. I don't know why that would have killed the power supply FETs, but that's a very interesting one. And I do wonder whether the TL494 itself is leaking voltage onto pin 4, holding it high, and by manually grounding it there, we are actually, we're kind of correcting the fault there. So, I mean, something smells. Oh, actually, something is getting really freaking hot. What the hell? Holy crap! I told you I knew I smelled fire. Fire in the booth. Boom! Something hot over here. Something's freaking stanky hot over here. What do we have? Is it a gate resistor? Boom! If it's a gate resistor, then that is because I have done a solder bridge because I am tired. Let's take a look underneath the board. I don't see a solder bridge here, my friend. I don't see a solder bridge here. So, why is that? What is it over here that's getting hot? There's a couple of capacitors over here that might be heating up. So let's take a look on our thermal imaging camera. Again, if it's a gate resistor that's getting hot, it must just be a solder. Wow, we have something getting to 76, 85, 85 degrees, 79. So something is cooking up at 82 degrees. Smells good over here. Yeah, is it a gate resistor, you know? Could be a gate resistor. Which could mean that the drive circuit is faulty, because if there's DC on this gate... Oh, there's something. We have 0.9 volts on that gate there, which is not ideal. So I think the drive circuit did do a poo-poo. Here we go. We have our 14 volts on this gate resistor here. So that is either a solder bridge from my tired ass hands, or it is a drive transistor that has itself done a poo-poo. Let's just run over with the soldering iron one more time, just to get rid of any solder bridges that I may have made on this jank-ass single-sided PCB that I don't give two flying Fs about. There we go. Bye-bye. Any solder bridges, you are not staying for dinner. You are not welcome. Okay, easiest way to check for solder bridges obviously is with the multimeters. Let's get the multimeter out on continuity mode. Okay, that's not continuity, that is just capacitors charging, which is good to know. That is capacitors charging the other way around. But we do have continuity here between 12 volts and the gate here. And it seems to only be on this set of pads here. It's really weird. Why do we only have continuity on that one set of pads? Oh, because the others have 100 ohm gate resistors. Yes, okay. Wow. You know what? There appears to be continuity here between these two pads, but I don't see it. I don't see it, and I've scratched it, and it's still there. So let's just run over with our iron. Just kind of flux it up in case there's anything we can't see with our eyes, but is actually there. Okay. Is it still there? What? 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 We have continuity here between these two pads, but... Oh, wait, maybe it's here. It's back a little bit. Maybe it's this bit right here. Yes, it's probably that bit right there. I was looking too far forward. There we go. Solder Bridge City. Welcome to Solder Bridge City. So now do we have our pulses? Did the drive circuit actually survive if I wasn't such a freaking dumbass with this sleepy nonsense? No, you know what? Pin 4 is still staying high, actually. Pin 4 is actually still staying high, even after we got rid of that. We have got rid of our parasitic current draw, so we're not drawing any current anymore from here. But let's take a look on our drivers. Could our drivers be causing the pin 4 to just be staying high? The Amp Lab did a complete teardown and repair of the A6000 GTI. Really? I saw their sort of teardown, but they didn't actually come through with the second part of the video, or at least they hadn't when I last checked, of the actual repair process. So if they've come through with that since, I would very much like to see that, because I'm very much struggling with the one I've got here. Ah, okay. So this would be the NPN. This is going to be the NPN drive transistor, and this is going to be the PNP. Oh, the PNP drive transistor has like 0.3 of a volt on it. That shouldn't be there. There's 0.3 of a volt on the PNP drive transistor. Yeah, that definitely shouldn't be there. So something has fucked itself in here. We have, look, we have some tiny attempts at drive on one of these gates. I think that the thing to do is to remove the drive transistors, because they're the next likely thing to go down. And then if removing the drive transistors doesn't do anything, doesn't change how the TL494 is acting, then we remove the TL494 itself and just replace that. Drive transistors we've got here appear to be the C1815 and the A1015. So let's just quickly drop those out of the board. Bust those out of here. Cut pin 4 off the board. No, then it's gonna... no, we're not gonna do that. Might as well just replace the TL494. It's easier than cutting pin 4 off the board. I can hot air the TL494 out in less than 10 seconds, probably. Alright, out you come. That's one. That's a number 2. There we go. So now that they are out, there's a few tests we can do. We can check those in the transistor tester. But first thing I am intrigued about is to just power the amplifier back up again and see if we get decent pulses now or not. 11.1 volts on here. Let's go. Let's go. Flip her over. Pins 9 and 10, what are you saying? Pins 9 and 10, what are you saying? With the remote cable in. Okay, pin 4 still high on the TL494 with the drive transistors removed. So the drive transistors probably survived. So our issue here is possibly going to be the TL494. In a pinch, we can ground the TL494, but it's not ideal because it causes the amplifier to come on instantaneously, like super hard, which is not what we really want to do. So we're not going to do that. We are going to take the TL494 out of the board. Going to see if that voltage on pin 4 is still there, and if it is, we're going to be looking for like leaking capacitors and stuff like that, perhaps. At this point, yeah, the repair is not worth it. Yeah, so this amplifier is already past the point where really it's kind of cost effective, like. But we're going to carry on just for the love of the information and just to figure out exactly what would be causing this. Is it TL494 that's dead, or... And yes, I do need to get myself a Hakko FR301. Can I find one in the UK at a decent price? No. I'm not paying the ridiculous £300 that they ask for them in the UK when they're only like 180 bucks in the US or something like that, or 200 or something. Bloody UK tax or UK pricing is nonsense. I'm waiting for one second hand to pop up, or somehow get one from the States with the 220 volt heating element perhaps. There we go, TL494 out. Let's, with the TL494 out and with no solder bridges on the back here, just to confirm. Make sure there's no bridges. Looks good to me. Just want to power it up again and just see if that 4 volts is still sitting there or not on pin 4 pad. Which would be upside down, would be that one there. 1, 2, 3, 4. Okay, you know what? It's actually not there anymore. So I think that maybe the TL494 was leaking that. 5, 6, 7, 8, 9, 10, 11, 12. They should be our 12 volts. Yep. So I think that the TL494 actually had gone bad and was actually leaking that that voltage onto pin 4, preventing it from coming on. So let's grab a new 494 from my drawer of requirements here. Let's bang that in. There we go. Cheeky bit of solder. Four, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, etc, etc. Okay. There we go. So now we should get our waves on pins 9 and 10. Please. Please. Please, why not? Okay. Now we don't have 12 volts. What the fuck? Why don't I now have 12 volts at the VCC? What the fuck? What's going on now? Solder bridge? No? Remote going in? Yep. This one should be our 12 volts turn on. This should be our 12 volts VCC, which now doesn't have anything on it. What the fuck's going on? What the hell? Necesito dormir. Necesito el cama. Ahora. why all of a sudden is this now deciding not to give me 12 volts VCC at the TL494 pins. Literally, all it did was change the freaking chip. Here we go, we can see here, this is our 12 volts from the battery, okay, at this point here. Then, on this side, this pulls it down in order to pass 12 volts onto this middle pin. Why are you now not working? Fine, I will bridge you over so that I force VCC there just for a minute, just to see if the 494 works now. So I'm just going to bridge 12 volts onto the TL494 for just a second. Now we have a lot of fucking random voltage everywhere. So much random voltage on the TL4. What the hell is going on with this? This is absolute nonsense. Never seen so much nonsense in the power supply section before. It could just be that I'm really tired and I'm just missing something really simple. Right, TL494. That is what I removed, isn't it? I removed the TL494, yes. Pin number 12. On the TL494, pin 12 is VCC. So let's flip this around. Pin 12 of TL494 is VCC. So VCC connects to 1, 2, 3, 4, 9, 10, 11, 12. Pin 12 connects to, yes, this transistor here, which I believe to be 12 volts VCC for this chip. Now, this hopefully shouldn't connect also to ground, which it does not, which is good. So this H649 transistor, that should give 12 volts to the TL494. Now ground on the TL494, where's our ground on the TL494? That is pin number 7. Let's test the transistors that I believe to be the drivers that we took out earlier. Let's just see if they're okay. NPN, that is fine. PNP, that is fine. So these drive transistors are just fine. So I'm just going to put these back in real quick. The drive transistors shouldn't really be affecting anything, but I just want to double check that they are not affecting anything to do with the TL494. It shouldn't be, but I just want to make absolutely sure by fitting them back in. Alright, drive transistors are back in. This is just going to want to turn into one of those ones that's just like stupid headaches for like no reason, and just probably I've probably made a solder bridge somewhere because I'm really tired or something. Right, TL494. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What we got? What we got? So on pin 1, we have. Actually, my remote cable isn't even in, so that won't help. On pin number 1, we have 0 volts. On pin number 2, we have 0 volts. On pin number 3, we have 0 volts. On pin number 4, we have 0 volts. Pin number 5, 0, 6. Yeah, so for whatever reason, now the remote turn on circuit is not working now for whatever reason. That's the problem I was freaking having. So what do? Do I change this VCC transistor perhaps? Let's change the VCC transistor. Maybe that's gone bad randomly just now. We do have the correct voltage going to the VCC transistor to turn it on. So it should be passing our 12 volts from the battery. Not too sure why it's deciding not to do so. Let's read what that reads in the transistor tester. If it reads normal, I'm just going to give up at this point. Oh, okay, excellent. It reads as something missing on pin 1. Excellent. Fucking awesome. So we can replace that. That is, what the hell is that? This is probably going to be a PNP transistor. It's marked with H649. So we need to replace that H649. So we can just quickly go to Google and just make sure. H649 transistor. Let's just double check what it is. It is a low frequency power amplifier. It's just a what are you? Are you PNP? Ah, here we go, PNP. So I can very easily replace that then with just a simple B772, 2SB772, nice and easy. Drop one of those in. Now, BCE is what we read on the board. BCE, is that the same layout as this one? No, it's ECB. BCE. So I need to flip this one backwards compared to what it is marked on the board. On the board, it's labeled as BCE 123 by the looks of it. So, yep, we need to flip that round. You see that? B on the board here got BCE, but this on the transistor tester is ECB123. So we just need to like turn it around the other way. So pin 1 on here is E. So we put pin 1 into E like this. Cool. Right, now this should come on and send voltage to the TL494 VCC in, 12 volts, power up. And let's see, pin number 12, 9, 10, 11, 12, we should have 12 volts on there. Yes, we do. Do we have output on pin 9 and 10? No. What do we have on pin 3? 0. What do we have on pin 4? 2 volts! Okay, so something is not right with the circuit which is responsible for softly, slowly turning on this amplifier. We have voltage leaking onto pin 4 of the TL494. Now, what is that? There should be some kind of capacitor, resistor, diode network kind of thing going on over here, which will be a soft start for this amplifier for pin 4. So as we can see here, there is actually a capacitor, which is just here, this big one here, which appears to have on one side of it, it has the 2.5 volts on pin 4. The other side of it, it has 0. So that is ground. So that is going to be the timing capacitor that's going to reduce the voltage on pin 4. Now, we probably have a leaky diode perhaps over here maybe. Let's have a look. We have, on this diode, we have 1.7. On the other side, we have ground. On this resistor, we have nothing either side of that. So where is this 2 volts coming from then? What else are we connected to? Let's flip the board over and run some traces. So it starts to sink down. If you check the scope, yeah, when we turn the amplifier on, we get it start to sink down, but then it kind of stabilizes out at 2.5 volts, whereas it should be sinking all the way down to ground, but it's not. So the traces that this is connected to, it seems to be just this capacitor, which is then grounded. I can't tell where that 2.5 volts is coming from. Let's just very quickly, because this is such a shitty amplifier anyway, and we can just solder it back on or put a new cap in. I'm just going to really quickly, just for joke's sake, just cut the leg of this capacitor here real quick, which is going to stop the discharge from pin 4, and that should help us to find where this leakage is coming from. Okay, so we still have the exact same scenario with the capacitor removed from there. So where is that voltage coming from? It's almost like it's coming from the it's almost like it's coming from the 494 itself. 2.5 volts still chilling there. This resistor should be 100k. Yep. This resistor should be 100k. Yep. This diode should read one way and not the other. 530 one way. The other way will read nothing, which is correct. It's a freaking ball ache. What the hell is this all about? You know what? Maybe we will just screw this and just put one of our own soft start circuits in, because it's going to be quicker. It's going to be quicker than trying to diagnose what the hell is wrong with this. Just to put our own soft circuit in, soft start circuit. It's almost so what's happening is that pin 4 is not sinking down to ground. So on pin 4 we should have continuity to a 10k resistor, or like some kind of resistor, which is going to be sinking the voltage down to ground through the capacitor. So where is the resistor that connects to pin 4 then? This capacitor is connected to pin 4. Oh, here we go. There's something over here. Okay, cool. So what is this resistor's value? This is a orange, yellow, gold. That is reading as potentially open. The multimeter is just charging and charging and charging. So if that capacitor has actually gone open, that resistor, if that resistor has gone open, then that will actually be preventing this amplifier from going to turn on. So let's just, I'm terrible with my resistor readings. So 4-band resistor calculator. Pin 4 DTC sets the dead time. Yes, it does. It does set the dead time, but if it's too high, it will be 100% dead time, causing no square waves on the outputs of pin 9 and 10. Which is what the case is here. We still have 2.5 volts on pin 4, which is preventing any duty cycle. So we have orange, orange, yellow, gold, which is, don't tell me because we're just going to figure it out. Orange, orange, yellow, gold. That should be 330 kilo ohms. That's freaking really high. Okay. Well, I can't even read that properly because there's capacitance in the board preventing me from reading that properly. For fuck's sake. Does that go to ground on the other side? It doesn't even go to ground on the other side. Maybe that's the problem. Maybe that should go to ground on the other side. Let's just check that resistor real quick and see what voltage we have when we're turning this on. So that is connecting to pin 4. So we have 5 volts on that side, and this side we have our 2.6 volts, which is preventing the amplifier from coming on. So that must be 5 volts. That's coming from the TL494. Okay, cool. I understand what this is doing now. So through this 330k resistor over here, it's providing 5 volts initially to the TL494 pin 4. Then what should happen is the voltage should then sink down to ground through some other resistor from pin 4. Yeah, it should basically be pulling the output of this 330k to 0 volts. But it's not. So we need to find whatever other resistor is connected to pin 4 here. There must be something else connected to pin 4 that pulls it to ground. Connects to capacitor there, resistor there. Ah, here we go. Oh no, that's just, never mind. That's just charging capacitor. Okay, there's a diode over here that is connecting to. Let's have a look over this side then. We have a diode over right at the top here. Or is it a capacitor? No, I think it's a capacitor. There's another capacitor over here that it connects to. Something over here. Okay, the negative of this capacitor over here, this big boy. So maybe this capacitor's leaking. .1, 2.8. Okay, what's on the other side of that capacitor? 4 volt. Okay, I reckon that capacitor might be leaking. I reckon that this capacitor could be leaking, which could be what's causing this problem. So let's pull that off the board. C23E. C23E. Okay, what's this supposed to be? This is a 16 volt 220 UF, or sorry, that's microfarad, isn't it? Yeah. So do I have something I can just quickly drop in place of that? Let's have a look in my capacitor drawers over here. What do we got? What do we got? What do we got? That is a 50 volt 10. This is a 16 volt 100. I could parallel a couple of these together. That would give me the same capacitance if I don't have the exact right one that we need. 50 volt 1 microfarad. No, too small. What's in this one? 10 microfarad, no. Okay, so 16 volt. Okay, we're going to parallel 2 of these together then to see if that makes a difference. That is the same, that is the correct the correct capacitance value. It's a bit small for a 220 microfarad, but it's only 16 volts. This is very low voltage capacitor, so it doesn't need to be that big. Let's just see whether the voltage has disappeared. Now that we've removed that capacitor, let's see, is that leaking voltage still there? Oh, it's not! It's not there anymore! And we have fucking drive! Yes! Fuck you! Fuck you! Now to get these paralleled, I'm probably going to have to do some janky as frick soldering. Maybe put this second capacitor underneath board and put it sideways. I don't know, something very freaking janky, because these legs are not big enough here, you know. I can't fit that in there to jankily, like, do I have a 220 microfarad 16 volt chilling around anywhere? You know, I probably don't even need to use the same. I could probably just use a 100 microfarad and it would be fine. What's this? No. Alright, let's just try my other capacitor drawer up here. Let's see if we've got anything useful in here. I'm looking for something kind of relatively small. Is not what she said. She did not say that. $100 microfarad, but it's 50 volts, so it's freaking massive. What's this one? That is a 470 microfarad. That's too big. Which is also not what she said. This is a 4.7. No. Nah, we're going to have to go with the janky parallel method. Donor board. We can see if there's one on the donor board. Yeah, alright. See if we've got one on the donor board. I doubt it though. It's a very specific value. 4.7. 4.7. Like, it's a very big low voltage capacitor. I don't think we're going to find one of those. $25 volt 100. Nah, it's such a random value. I think we're just going to parallel it up. I can't be asked to look any longer. We're just going to parallel these up. So I'm going to stick one in the board normally. This is such a crappy amplifier. You know, this repair wasn't even worth it for what the amplifier is. But hopefully it was worth it to see me like faff around looking for a shorted capacitor for however long. Right, now which one's positive and negative? Negative is going to end up on the top here, I think. Yeah, negative's going to end up on the top. Sorry, yeah, negative's going to end up on the top when we flip it over. Okay, cool. That's what I've done. Negative. Oh no, I haven't. I've done negative on that side. What the fuck? Oh, positive. No, wait. Which capacitor did I just replace? This one. I just replaced this one, didn't I? C23E, I just replaced this one. So positive is that one. So positive is going to end up on the top. Okay. Now let's see what happens. When we fire her up, we should have PWM on the gates. Gentlemen, let's see. Oh, yes, we do. It comes on very slowly, which is what I like to see. Good stuff, good stuff. And it disappears very slowly as well by the looks of it. Yeah, awesome. Good stuff. So new MOSFETs then. And we should check the output section too. The dead time ends up pretty low actually on this bad boy. Yeah, which would make sense. We got high value gate resistors. So what is the dead time on this? Time for probe 1 duty cycle is only 40%, which means that we still have a little bit of DC voltage on pin number 4. If we zoom in on pin number 4 here, VRMS, if we zoom in on pin number 4, you can see here that we still have a little bit of voltage on there, which will be preventing 50% duty cycle. But that's fine. This is a small amplifier and we've got high value gate resistors, so it's going to switch softly, which should prevent noise in the rest of the amplifier, so I'm not too bothered about that. It's absolutely fine. So just quickly then, let's check the outputs, make sure that they aren't shorted. Seems good so far. Channel 1, 2, 3, 4. Yeah, the output section seems to be just a-okay, so I reckon we can lump in a bunch of new power supply FETs from my cheeky power supply FET drawer just over here, and this should be ready to go, and I can finally go to bed, which is voy a la cama, voy a ir al cama, voy a ir al cama. Voy a dormir en unos 5 minutos. How much is it going to cost to fix this? Fuck, I don't know. I'll work that out tomorrow, but probably not worth what this amplifier is. Los caps son baratos. Baratos, is that cheap? What's expensive? I think is expensive claro or something like that in Spanish. How do you say cheap in Spanish? I'm pretty sure it's something. Cheapo. Cheap is barato. Barato. Do you emphasize the do you emphasize the A, like barato, or do you emphasize the second A? Do you emphasize the first A or the second A? So is it barato or barato? I think it's probably barato. That sounds more Spanish, doesn't it? I think in Spanish you tend to emphasize like the second vowels. Like sandwich is bocadillo, which is you're emphasizing this kind of second. You don't say bocadillo, you say bocadillo. Or sacapuntas. You emphasize the O. Huh? Barato. Oh, okay. Barato. Su novia es barato. Barata. Maybe, I don't know. Does it change with gender? So if you want to say su novia es barata, is that right, or is it su novia es barato? Or tu novia. It's not su, is it? That's a bit too formal. I proper freaking suck at Spanish, so I have no idea. I haven't done it since high school. I took Latin as well. I actually really enjoyed Latin, but I only took it in my first year of high school. So I was year 7. I was probably about 11 years. No, what was I? Yeah, maybe about 11 years old. I took Latin. I pretty enjoyed it actually. It was pretty cool, pretty good. Yeah, there weren't enough seats to take it for year 8, which was. I actually got good grades in Latin. I actually got like A's and stuff in Latin. It was pretty cool. Okay, provided we have no solder bridges, this should be good to go and should power up. Shall we see, gentlemen? Shall we see? Tu novia es barata. Okay, yes, it is an A. It does change with gender. I assumed it probably would. Tu madre es barata. Tu madre es muy barata, pero me gusta. Alright then, test time. What are we saying? Is it going to work? 5. Oh, okay, we have excessive current draw, which means that I probably soldered a bridge somewhere. Let's check it out. Where do we have a potential bridge? Really? I couldn't see anything. Yeah, well, we have a continuity, so let's go through every single one of these. Not there. 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 Ah, there. Right at the back of that. Right at the back of that. Check that out. Right at the back there. I'm trying to rush this and do it as quick as possible because I need to get to bed. Shoot, it's fucking, it's 25 past 1 already. Can't believe it. Can't believe it. Oh, come on. Why? Why are you drawing excessive current? For fuck's sake. Right, here's the gate drive. Gate drive looks good on that bank. Gate drive looks good on that bank. Oh, does it? Not so much. Gate drive looks... What does it look like on that bank? So we have gate drive on that bank, that bank, that bank, that bank. 1, 2, 3, and 4. Let's go to the other side. Okay, no... Oh, wait, hang on a minute. Gate drive on that bank, that bank, that bank, and that bank. Okay. So then... are we building rail voltage? Let's have a look. Are we building rail voltage? Do we have negative rail? We don't appear to have positive rail. Okay, so we're not building positive rail. No, we're not building positive rail. Okay, fuck. Why are we not building positive rail? Let's turn our attention very quickly to the rectifiers. Let's see if we have a short on any of the rectifiers or any of the rail caps. The capacitor was bad earlier, so we could have a shorted rail cap perhaps. So let's check a continuity between the rectifiers right here. That is reading the transformer wind. That is reading capacitor. There we go. There is a short here. So this here shouldn't be shorted. This is shorted between all 3 legs. So the first thing that we're going to try and do then is we're going to try and remove this and see if it's the rectifier. Fucking one thing after another. I just want to be done with this. This is pretty simple now, guys. Provided none of the outputs are shorted. It could be a shorted output. If it's a shorted output, man's going to bed. But if it's a rectifier, I'm just going to quickly replace it and get it running. Is the short removed? No, the short is not removed. Low side, high side. None of the outputs are shorted. So that means it must be maybe a rail capacitor, which is just one of these 2 yellow things here. So you can see we have a short across that one. That one's okay, so let's just quickly remove this rail capacitor. It's going to take me 2 seconds, especially with a bit of hot air. Crank my soldering iron up. I've got it at 390. We're going to go all the way up to 480. It's full send. Full send. Big trace. And we are also breaking CA glue on the top. So that's why it's coming out quite tricky. Because we are breaking the CA glue bond on the top of the board here. As well as the solder. Right, there we go. Cap is out. Cool, cool. Has the short disappeared? No, it has not. What else is there? There is this tiny little capacitor here. There is a tiny little film capacitor just right here. Let's just quickly lift that. Make sure that hasn't shorted. Nope, so there is a short somewhere else on the board on the positive rail. Shall we quickly see what it is? There's a very quick way to see what it is. Very quick way to see what it is. We take our power wires. we bang them on these traces right here. Let me just check which one's going to be positive. That's going to be that one, so I don't backwards feed any voltage to anything that I don't want to. And we put the negative on this one. Wait for that to cool down. It's already fucking cooled down. Come on, stay on the trace, stay on the trace. That's it, cool down, grab, 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 grab. Oh, why is this so shitty? I'll fucking go to bed. Literally, why are you not taking? Right, so we put our power supply wires there, we flip the board over, we turn the power supply on with a high current, and we see what smokes. Gentlemen, we see what smokes. Turn the power supply down to start with, nice and low. So we have 0.3 amps being drawn so far. Let's crank up the brightness on this again because it has reset itself once again. And let's start turning up the current. Okay, it's a very, very short because we have 6 amps already here and we are at 0.3 of a volt. So it is a very, very short. Whatever the short is, it's very, very short. If that makes any sense. There's a big hot spot over here, but that's just where I've been soldering. This is a very, very short. We have 10 amps and only 0.5 of a volt. And we can use that to calculate the resistance of this short. So we have 0.5 of a volt and we have 10.3 amps, which means that this short is 0.048 ohms. I can't see anything getting hot other than the area that we just soldered. Like the area that we just... Nah, we're gonna full send it with 20 amps. I am bored of this now. Full send, 20 amps. I can't see anything really getting hot apart from the area that we just soldered. So yep, 20 amps, let's go. There's something over here getting nice and hot. Here we go. Now we're starting to show. Okay, well maybe there's a bit of solder over here that's not supposed to be here. See this? That was getting really hot. So let's just try and reflow that. Although these, although these are just jumpers, so maybe they are supposed to. Maybe these are just getting hot because this is the highest point of resistance here. Still got the same short, so let's cook it up even further and see what gets really hot. I'm just going to leave it cooking until something starts smoking, fuck it. I don't want to kill my bench supply though, because that won't do 20 amps continuously for a long time. It's like these traces. These traces themselves are just getting really hot. It's so weird. Who thinks I should just connect it to a car battery and just BOOM! Blow open whatever the short is. Oh hey, hang on a minute. The short has just gone down in resistance. We now have the short has gone up in resistance. We now have 1.2 volts with 9.8 amps. So whatever soldering I just did then has increased the resistance of that. Weird. Okay, so that's the short disappeared now. If I lift that, that's the short disappeared, but why? You know what I think? This could be a board design fault or something. This is weird. It's almost like that bit of solder's not supposed to be there. What the fuck? So by lifting that, by lifting these jumpers, we now don't have a short anywhere, naturally. Okay, fine. But we need to get rail over here. Positive rail needs to be here, which is, I think, this is it this one? I don't know, fuck it. This one here is positive rail. So this one needs to connect to this, which goes down to here, which goes down to one of these, maybe? That doesn't seem to connect to anywhere. That trace doesn't seem to go anywhere. It's just on the top of the board. Yeah, I removed the solder bridge from the TL494 workings. Don't worry about that. Okay, so we're coming out of this rectifier. Positive rails coming out of this rectifier, going to this trace, which is then going up to here, which should then be going up to the rail capacitor. So that all looks good so far. We have continuity to this trace here, going up. So do we have a short between here and the rectifier? No, we don't. That looks good. Okay. So maybe I'll just solder that back down then. Like, with that removed, everything checked out okay. As in, like, ready for it to go back in, kind of checked out okay, you know what I mean? Right, okay, so they're now soldered back down, as they were before, into the base as well, into the back here. Let's solder that in from the back. So it wouldn't make sense now if there's a short. There isn't! What the fuck? What? What? Just soldering back in everything that I took out, including Mr. Rectifier down here. So this has got nothing to do with the TL494. This is just a solder bridge that like was on the board anyway, somewhere further up into the output section here. Nothing to do with TL494, nothing to do with power supply circuit. Fucking hell. Maybe some wire or some solder fell onto the board while it was in operation. The heat from the short circuit caused the solder to melt onto the board, making it look factory, killing the power supply circuit, killing part of the 494 as well. Right, everything's soldered back in. Now you should come on, my friend. There's no short on the rails anymore. We double checked. Oh, we triple cheeseburger checked. We triple cheeseburger checked. Power supply down. Voltage up. 10, 13 volts, 3.9. Right, power supply has come to life. Yes. Gate drive looks fine. We have positive rail, negative rail, and do we have positive rail as well? Yeah, we have positive rail. Do we have any audio? Very quickly, last check, is there audio? And if there is, if there isn't, I'm going to bed regardless. Input is the ones closest to the LEDs. Flat in the middle, flat in the middle. Input level up a little bit from 6, up a little bit from 6. Frequency doesn't matter, bass boost down. Oh, bass boost was fucking cranked. Oof, ha, le clip, clip. Oh, fucking hell. That wave looks absolutely horrendous. Fucking hell. Output section is fucked as well then, but it's not fucked, it's just shit. What the fuck is wrong with that? Are all the channels like that? All the channels are like that. Why are all the channels like that? How can all the channels look like that? What? Dude, this looks even freaking worse. I'm just using my floating signal generator here. It looks even worse. Oh, but look, there's actually looks like what appears to be a vented capacitor up here by the RCAs. So I reckon that could be a vented DC blocking capacitor, because there was some DC on the sine wave here going into the op amps. Yeah, look, there's a bunch of DC chilling there. What the fuck? Oh man, this amp, man, fucking hell. Oh, right. Well, it looks okay up to kind of clipping point, right? It looks kind of okay up to this point. I reckon this could just be actually how the amplifier is designed. And then only when it starts to clip does it start to look really, really bad. Oh, fucking hell. I don't even give a shit about this anymore. I think this is probably just how it is. I do not even care anymore about this amplifier. That's probably just how it is. This is such a cheap, nasty amplifier. That's probably just how it is. Although surely not. Like, what the fuck, man? But, alas, I cannot be fucked to do anything more with this, so it is what it is, and they just have to deal with it. It works again now. This is not something worth going any further with. Sine wave looks fine at the op amps, and the fact that it's the same on all 4 channels, that just tells me that could probably just be how this amp's freaking designed. Because, like, if it was... So the op amps, it's not going to be that. It's not going to be the op amps. It's not going to be a single capacitor on the input. All 4 channels are exactly the same. And inside on this PCB, we have 4 separate amplifiers on one PCB. Nothing about these 4 channels shares any components that would fail to cause that problem. So this is just how it is, gentlemen. I am tired. Thank you for joining. It's been a pleasure. Hope the stream's been somewhat enjoyable, somewhat really fucking annoying, and I will see you in tomorrow.